Okay, good morning. So today we will talk about the principal ideal domains, and if time permits, we will also talk about the unique factorization domains. But before we go into that, last time I made a mistake in the proof of theorem 1. So let me start by correcting this. So those of you who've seen the notes I posted, I already fixed it there. Correction to theorem 1 last time. Okay, so the theorem 1 was formulated as follows. So let R be a commutative ring with unity. So let R be a commutative ring with unity. Then the ideal in R, then the ideal I in R is maximal ideal, is maximal ideal if and only if R over I is a field. Is a field. Okay, so as for the proof, the opposite implication we have proved last time, and that's quite easy. And in the proof of the direct implication last time, I made a typo in the definition of an ideal J. And as you correctly noticed, this then it's not immediate that this J is includes I. Okay, so let's redo the direct implication really quick. So assume that I in R is a maximal ideal. I in R is a maximal ideal. Maximal ideal. And so kind of it is immediate that the quotient is a commutative ring, right, with unity and so on. So the only thing we need to prove that every non-zero element has a multiplicative inverse. So need to show that every non-zero A in R over I has multiplicative inverse. Inverse. Okay, so let's take A, which will be the coset containing X. So that's the element of the quotient ring. Be the element of the quotient ring. Such that X doesn't belong to I. Okay, so just note here that in this case, X plus I is not I, which is the identity, which is the additive identity in the quotient ring. From here, it follows that A is not 0 in the quotient ring, R over I. Okay, so now consider the following set. Consider the following set. Set J, and it will be constructed as XR plus I. or to be precise, that's the set of all elements of the form x times r1 plus I1, where R1 is in R and I1 is in I. So let's just consider the set of all possible kind of expressions of this form. Okay, so the first kind of claim, which is basically immediate, claim 1 is that J with respect to the binary operation plus forms an abelian group. Is an abelian group. Okay, so indeed, if we look at the set, what do we have? So first of all, the 0 is in J. 0 is in J, right? That's just x times 0 plus 0. Now the second thing, if we have some element, x times r1 plus I1 belongs to J, and from here it follows that minus this element, xr1 plus I1, can be written in the form as x multiplied by minus r1 plus minus I1. So this guy is in I, this guy is in R. So the whole thing must be in J, just by the definition of J. And of course, it's closed with respect to addition. I1 belongs to J, and xr2 plus I2 belongs to J. Then their sum, x times r1 plus I1 and x times r2 plus I2 can be written as x multiplied by r1 plus r2 plus I1 plus I2. Again, this guy is in R, this guy is in I, so the whole thing must be in J by the definition. Okay, so J with respect to the binary operation plus forms an abelian group. Now the interesting part is that if we look at the product of J with R, it must be in J. So in other words, J is actually an ideal over ring R. So let's look carefully at this claim 2. Let's take any element J1, which will be written as xr1 plus I1. That's in J. And let's look at the product of J1 times, say, R2. And J1 times R2 is the following thing. So this is x R1 R2 plus I1 R2. Well, now obviously the product of R1 R2 is in R, right? But now the nice thing is that I is an ideal. Hence the product of I1 and R2 is in I. So this whole thing belongs to J. Okay. So now from claim 1 and claim 2, we know that J is an ideal. Now from claim 1 and claim 2, we know J is an ideal. Just from the very definition of J, we know that I is a subset of J, right? Because if you take R1 equals to 0, then every element of I is in J. And we also know that there exists an element X, which belongs to I and doesn't belong to, which belongs to J and doesn't belong to I. J, and it doesn't belong to I. That was the element from which we have started. So from here it follows that this inclusion I in J is strict. And of course J is a subset of R. So in other words, J is an ideal strictly larger than I. Yeah. Larger than I. And because I is maximal, the only way this can happen if J equals to R. Because I is maximal, meaning there is no strictly larger proper ideals containing I. This implies J equals R. J equals R. Well, in particular, because R is a ring with unity, in particular, the unity over ring R must belong to J. Well, from here it follows that the unity, that there exists R1 in R and I1 in I, such that the unity can be written as XR1 plus I1. Well, but then if we multiply two things in the quotient ring, namely the coset X plus I and the coset R1 plus I, then what we will get is the coset containing XR1, right? And that will be the same as the coset containing 1. Now, this thing here is A. This thing here is unity in the quotient ring, R over I. So what we actually did, we found an inverse. We found a multiplicative inverse of A. So, in other words, we found a multiplicative inverse of A. Okay, so that concludes the proof of the direct implication, and that fixes the bug I made last time. Sorry about that. So last time I messed up the formula for the J. So the multiplication, the brackets there was the brackets in the wrong place. So sorry about that. Okay, so now let's move on to the principal ideals. And first, let's recall where we stopped last time. So we introduced the generating sets for ideals. Okay, so last time that for a commutative ring with unity, or a commutative ring R with unity and arbitrary subset, S in R, we have defined an ideal generated by S. Find an ideal I generated by S, which is S included, which we denote as S included in the round brackets. are an ideal generated by S. And this was the smallest ideal containing S. S. Okay. Then we have sketched the proof of the following lemma, that one can describe the collection of all elements in S as follows. Then have root, well, say stated, and sketch the proof of the following lemma, that when, let's say, S for simplicity has only finitely many elements, but of course the lemma will be true for arbitrary collection of elements, for arbitrary subset. Okay, so let's suppose that S is a finite set. Then what you can say is that this ideal generated by S, so as a set is the collection of all elements in R, which can be written as A1 times R1 plus A2 times R2 plus etc. plus AN times Rn, where this R1 all the way to Rn, they are elements over ring R. Okay. So in other words, if we have elements A1 to AN, then the ideal they generate in the commutative ring with unity, that was important. That R is commutative with unity. With unity, otherwise this will be much more complicated, of course, than written here. And here it's a good kind of place to make a remark on terminology. So what you will find in the book is that this set S is then called the basis of an ideal I, because of the lemma above. Book calls A1 to AN to be basis, of ideal I. Well, but this is slightly misleading terminology. Misleading terminology because kind of these coefficients R1 to Rn, they are not uniquely defined, because coefficients R1 through Rn in R are not uniquely defined. So in other words, in general, it can happen that a1 times r1, of course, all the way to an times rn equals to a1 times r1 prime plus a2 times r2 prime plus etc. an times rn prime for two different n tuples of coefficients. And that's why this terminology is largely abandoned nowadays. Which is largely abandoned nowadays. So we will call a1 to an a generating set. Rating set of an ideal a1 an to avoid kind of this misleading terminology. Okay, so now kind of the ideals which can be generated by a single element, they play a very special role, and they called principal ideals. Let's talk about the principal ideals. All ideals. So let's introduce the definition. So we say that, so again, say that I in R is principal if it is generated by a single element. If it is generated by a single element. So in other words, there exists an element A in the ring R such that I is an ideal generated by A. Now this is kind of the principal ideal is an analog of cyclic subgroups. In the context of rings. However, now generated means different thing, right? Generated as an ideal, not just as a group. Okay, and not every ideal is principal, and we can actually easily construct a non-example. Let's say non-example 1. So here let our ring be the ring of polynomials with integer coefficients. And let's take an ideal generated by 2 and x. Explicitly, this I, right, it's the set of all polynomials which can be written as 2p1 plus x times p2 for some polynomials p1 and p2 in z of x. And if we want to be even more explicit, we will say that these are the polynomials of the form C0 plus C1x plus C2x squared plus all the way to Cn x to the n, where this n belongs to non-negative integers. And of course, C0, Cn are integers, but what's most important is that C0 is even. 1, 2. So the set of all these polynomials forms an ideal, which is precisely the ideal generated by two polynomials, 2 and x. Okay, so now the claim is that I cannot be generated by a single element. I cannot be generated by a single element. And indeed, for the sake of contradiction, suppose that I is generated by P, by a polynomial P, P of x, which would be like B0 plus B1 x plus Bn xn. And here B0 is even, right? Because P of x must belong to this ideal. Well, then there's essentially two cases. So there's a case 1 when the degree of P equals to 0. Degree of P of x equals to 0. Then what do we have? Then this is just a constant polynomial. P of x equals B0 is an even constant. Is an even constant. And from here it follows that x cannot belong to an ideal generated by P of x. So it cannot generate the entire I. Because if you take an even constant and multiply it by any other polynomial, right, what you will get a polynomial of which all coefficients will be even for sure. Okay, so now let's look at the case 2, when the degree of P of x is greater than 0. Well, then what you can say for sure is that if you multiply it by any other polynomial, because Z is an integral domain, the degree can only go up. And then there is no chance you can generate, you can get to 2. You can get 2. So 2 will not be in the ideal generated by P of x. Okay.
In
Yes?
the line above, should it say x is not in the ideal generated by?
Oh, yeah, of course. Yeah, thank you. Thank you. Yeah. So in both cases, we cannot generate I by a single polynomial. Okay. Well, on the other hand, of course, there exist ideals generated by a single element. And let's look at the example 2. Example 2. So here let R be the ring of polynomials with rational coefficients. And let's look at the ideal, which is generated by 3 elements. And let's say that it will be x cubed minus 1, x squared minus 1, and x minus 1. Okay, so then actually, this ideal can be generated by a single element x minus 1, and it is a principal ideal. It is a principal ideal. Okay, so this example, is a manifestation of a general statement that actually of a general statement, which we will call theorem 2. So, which is formulated as follows. So let F be a field. Let F be a field. Then every ideal in the polynomial ring over F is principal. And the proof would be essentially based on the division algorithm. So let I be an ideal. Then if I is trivial ideal, is trivial, well, then it is generated by a single element, right? And we can say that I is an ideal generated by 0, and we are done. Otherwise, there exists a polynomial of minimal degree in I. Polynomial of minimal degree in I. Polynomial, let's call this polynomial to be P of x. Let's say this is P of x in I, minimal degree in I. Now the claim is that this is actually the generator of the ideal. So claim for all polynomials f of x in the ideal, f of x must be divisible by the polynomial P of x. Well, indeed, by division algorithm, what we have is that we can write f of x as the product of q of x times p of x, right, plus the remainder term, where either the remainder term is 0, x is 0, or the degree of the remainder term is strictly less than the degree of p of x. But the second case is impossible. Well, because then this polynomial r of x, which is written as f of x minus q of x times p of x, must be an ideal as well. All right, so this f of x is in I, right? This p of x is in I. This is in our ring R, and because I is an ideal, their product also must be in I. So this whole thing must be in I. And this would be a polynomial in I, which have strictly smaller degree than p of strictly smaller degree. And that's impossible because we have started by taking p of x of minimal degree in I. Okay, so here we go. In the ring of polynomials, every ideal is generated by a single element. And here we must put a remark that note that it is essential that f is a field, and that we consider polynomials only in one variable. That consider polynomials only in one variable. So mind the non-example 1, where we had polynomials in one variable over z, and then there exists ideals which are not principal. And let's also look at the non-example 3. Non-example 3. So now let's look at the ring of polynomials over a field. Let's look at the ring of polynomials over a field, but in two variables. So let R be a ring of polynomials over Q. It will be polynomials with rational coefficients in two variables x and y. And then the ideal generated by x and y is not principal. Is not principal. So you can basically prove that using the same method as we proved non-example 1. Okay, so now we are ready to formulate. Now we are ready to formulate another important theorem about the structure of ideals in the polynomial ring in one variable over a field. So we just proved that it's always principal. So now the question is, can we describe all maximal ideals? All maximal ideals in f of x. And it turns out that we can, because the maximal ideals are precisely the ones which are generated by irreducible polynomials. So let me formulate theorem 3. A non-trivial ideal P of x in the ring of polynomials over a field is maximal if and only if P of x is irreducible. And only if P of x is irreducible over field F. Okay, so the proof is not really conceptual for this one, so I might save some lecture time and leave it as a home reading. And that's theorem 27.25. Okay. Instead, let's talk in details about the corollaries of this theorem. So the first corollary would be the following, that let P of x be a polynomial in f of x, again f is a field, and let P of x be irreducible. Well, then if you look at the quotient ring R, which is f of x quotient by the P of x, quotient by the ideal generated by P of x, then it must be a field. Right? Because this ideal P of x is maximal, and by theorem 1, the quotient over ring by the maximal ideal is a field. Well, now because every field is an integral domain, corollary 2, we get corollary 2. So again, let P of x in f of x be irreducible. Well, then what we have is first the quotient R f of x quotient by P of x is an integral domain. Is an integral domain. Well, which immediately implies that the ideal generated by P of x is prime. And that's theorem 2 from last time. Okay. And finally, we will get the corollary 3, that if irreducible polynomial polynomial P of x divides R of x times S of x, then either P of x divides R of x, P of x divides R of x, or P of x divides S of x. And remember that we have stated Now, mark we have stated corollary 3 without proof 3 lectures ago. When discussed division algorithm. And factorization of a polynomial into product of irreducibles. And it was needed for uniqueness. So now we can complete the puzzle. Now we can complete puzzle and prove that every p of x in f of x can be factored in essentially unique way into irreducibles. Okay, and this brings us to the following story about the so-called unique factorization domains. So in the remaining half an hour, let me talk about unique factorization domains. Unique factorization domains. Okay, and that will be the definition. So an integral domain an integral domain D is a unique factorization domain, or UFD. Unique factorization domain UFD for short, if the following two conditions are satisfied. So first of all, if every element in D and let's say D small in D, which is neither 0 nor a unit can be factored into product of irreducibles. And the second part is that if this factoring is essentially unique, which would be as follows. So if P1, PR, and Q1, QS are two factorizations, of the same element, are two factorizations of the same element, then first of all the number of factors coincide. So then R equals S, and you can say that Q1 to QS can be reordered such that Ri becomes Ui times Qi, where Ui is a unit. Ui is a unit. So this factoring up to this multiplication of elements by, after multiplication of factors by units, is essentially unique. So this whole thing means that factoring is essentially unique. Okay, so in examples of U of D, we are already familiar with. So example A, the ring of integers is a UFD. So recall that every integer can be factored into primes, turned into irreducibles, and that's plus minus prime numbers. That's P in essentially unique way. And essentially here means that we can move this plus minus 1 around. So for example, if we have 49, right, we can write it as 7 times 7, but at the same time we can factor it at minus 7, and that's the only freedom you can have. You can move this units around. Well, and example B, so F for a field F, f of x is a unique factorization domain. So, and here irreducible numbers play the same role as primes in Z. Oh, irreducible polynomials. Reducible polynomials play same role as primes in Z. Okay. So now there is a kind of general statement that if you have the so-called principal ideal domain. So by the way, any questions so far?
So is it pi equals to ui times qi in the...
Oh, pi, yeah, thank you. Of course. So these factors, they coincide up to multiplication by the units. Thank you. Okay. So we say that an integral domain is the principal ideal domain, is a principal ideal domain principal ideal domain or PID for short, if every ideal is principal. Let's say that this is D, every ideal I in D is principal, namely generated by a single element. And there is a wonderful theorem. Which probably I'm not going to prove in details. I'll just put the statement that first of all, before actually we formulate, let me just put a remark that note that both example, both Z and f of x are actually PID, principal ideal domain. And the theorem states that in general, if you have a PID, if D is there's like two things. If D is a PID, then from here it follows that D is a unique factorization domain. So you can talk about this unique factorization, essentially unique factorization, into the product of irreducibles in every principal ideal domain. And what is even more kind of surprising, that if you have a unique factorization domain, D is a unique factorization domain, and from here it follows that the ring of polynomials is a unique factorization domain, UFD. And so this is theorems in section 45, proved in section 45. So I won't go over the proof because it kind of it involves slightly more advanced machinery. But I mean, if you're interested how it goes, you can take a look in the text. So instead, let's look at the corollary. Let's look at the corollary. So if we have polynomials over Z in n variables, n is a UFD, and if you have a field and polynomials over a field in n variables, then it is a UFD. So we can talk about factorization of multivariate polynomials, into product of irreducibles. And that's kind of that's the main point. So you can talk about the multivariable irreducible polynomials, and you can talk about factoring them into reducible, and still the irreducible will serve the same role as primes serve in the ring of integers. Now, probably the last really thing I wanted to say is something about Noetherian rings. So that's rings. Okay, so definition. We say that a ring R satisfies ascending chain condition. Ascending chain condition, or equivalently is Noetherian. If for every ascending chain of ideals in R. So let's say that we have I0, then we have I1, then we have I2, etc., and all the way to infinity. There exists n such that in plus 1 coincides with in. In other words, there is no there can exist no for a given ideal I0, there can exist only finite strictly ascending chain. Okay, so kind of the prototypical example of a ring which satisfies this ascending chain condition would be the ring of where all ideals are principal. So example, f of x is Noetherian. Well, indeed. Suppose that you have this sequence of this ascending chain of ideals, and because every ideal is principal in f of x, it's generated by polynomials, let's say Pn of x, right? So then what do we have? We have that P0 of x is included in P1 of x, is included in P2 of x, etc. Or equivalently, P1 of x divides P2 of x, P3 of x divides P2 of x, P3 of x divides P2 of x, etc. Well, because if you start with a given polynomial, right, each time you divide, you take some factor of that which has strictly smaller degree, right? You can this can happen only finitely many times, so cannot exist an infinite strictly ascending chain. Ascending chain. Chain of ideals.
Oh, should say P2 divides P1, the top.
P2, oh, yeah. P1 divides P0, I made a typo here, then there should be P2 divides P1, right? Then P3 divides P2, etc. Yeah. So they input kind of the next one divides the previous one, right? Because P1 should be in the ideal generated by P2, right? And this means that it's P2 times something. So this equivalent P1 of x equals to P2 of x times some r of x. Now the nice theorem, which I won't prove, of course, either, would be the following. If R is Noetherian, and then so is R of x. In particular, if we look at the ring of polynomials in many variables, then is Noetherian. Okay, so I'll probably I'll probably stop here because this is basically everything I wanted to say today, and I definitely don't want to go into the proof of that. Just to give you kind of an idea that there is much more to continue in abstract algebra. That's usually studied in details in the second course of abstract algebra, and of course in the graduate course of abstract algebra. And on the next lecture, we will talk about on the last lecture, we will talk about the algebraic varieties and ideals. So we will talk about the relation between algebra and geometry. If you have any questions, please ask. Otherwise, I'll just stop recording and continue with office hours.
Thank you, Professor.
Thank you.